Let's elaborate further this hypothesis testing using medians, and we gonna go and do this example 5.18 to demonstrate it further. This is the example from Ott's book, and here the sanitation department of a large city wants to investigate ways to reduce the amount of recyclable materials that are placed in city's landfill in order to prolong the life of the landfill site. And from an analysis of the recycling records from other cities, it is determined that if the average weekly amount of the recyclable materials is more than 5 pounds per household, then recycling could be profitable. To determine the feasibility of this recycling plan, a random sample of 25 households, sample size is 25, so we collected these amount of recycling materials from 25 houses, and when we plotted them in this box plot, we see there are too many outliers here. The box is shrink, and we have these big numbers here, so that are causing the skewness in the data. So this data seems like uh, positively skewed, and the kurtosis is also higher. So in order to confirm further the normality of this data, we do another plot which is called as normal QQ plot. Normal because we're testing for the normality of the data set using this plot. QQ means quantile versus quantile. So we have sample quantiles versus theoretical quantiles. Sample quantiles are the actual numbers, and theoretical are if this data set would have been a normally distributed data set, and then a perfect normal distribution should have the quantiles like this, and we have theoretical quantiles on x-axis and these sample quantiles on y-axis. A perfect normal distribution should have been a straight line over here, and all data points should have been on that straight line. So here the straight line is there, but it's relatively low, and we see there are many data points that are off from this straight line, so that data set seems like not normal. So what we do over here is we decided that we're gonna do it with the non-parametric approach, the test hypothesis test for the median. And first we will do it as a two-tailed test. We will use this confidence interval approach for the median, and in order to do that we need to determine the lower confidence interval for the median, ML, and MU for the upper. That we can get it from the numbers, and we decide those numbers based upon the table. It's table 4, and over there we have those percentiles, and those percentiles are actually they help us to determine which number to choose for in this sorted list of numbers, which number to be chosen as the number for this lower confidence interval. So that will determine on this L alpha by 2 is equal to C alpha 2 two-sided. Look into this line where it says two-sided in the table, and we look for this N. The sample size is 25 here, and plus 1 to it, so this will give us the number for this lower confidence interval. And then for the upper, it is given by N minus C alpha 2 N, and that will give us the upper one. Let's pick up those numbers from this table, and this table 4 in Art's book, and over here we have two rows. So these are the percentage points for confidence interval on the median and the sign test, and the thing which we are collecting here is this C, that will give us those percentage points or percentiles to be picked from these numbers and determine the lower and upper confidence intervals. Since our alpha is 0.05 and we are doing it as a two-tail test, so what we're going to do over here is we will go in this row, and here we see 0.05 is written here. So our numbers are here in this column, and if we are doing it as a one-tail test, we would have been looking the numbers here in this column. and our sample size is 25, so that's number 7. Now we get back and we see that here that number is 7 and we add 1 into it as per this formula. So 7 plus 1, that's the eighth number here in this list on this position, so that's 3.9. So that will give us our lower confidence interval, L at 0.025. We said L at alpha by 2, so that will become, since alpha is 0.05, so it becomes 0.025. C at alpha to n, so that means C at 0.005 and n is 25. So in the table the number was 7, so we'll add 1 into it, and this is 7 plus 1, the 8th number in a sorted list of numbers. So we sort these numbers, and what we can see over here is this 8th number, the position number 8, as a value 3.9, so that will give us our lower confidence interval. And for the upper, it's n minus c into this alpha two-sided and n, so that is 25 minus 7, so that's the 18th number. The 18th number over here is this number, 6.7. So the confidence interval which we construct from this is that it falls between 3.9 as lower and 6.7. So we are 95% confident or certain that the true median is in the interval 3.9 to 6.7. We can get it with the binomial thing also, and the exact solution returns this confidence level is in fact 90.957, that's 95.7% certain that the true median is 3.9 to 6.7. And so we got our confidence intervals. So now we do our hypothesis testing as H naught median is equal to 5 versus HA median is not equal to 5. We can also use this binomial formula to get the exact solution. That will be 1 minus 2 into binom dot dis, the Excel function. That is to find this location for this number. 7th in the list, and total numbers we have were 25. The probability we put over there is 0.5 and true in order to get the cumulative value. So we can use this confidence interval to do a two-sided test by simply checking if the hypothesized number and the number under the null, so the median under the null, if it is there in that interval, then we will fail to reject. If the number under the null, hypothesized number, is there in the confidence intervals, then we will fail to reject the null hypothesis. In our case, the median under the null is 5, so that is included in these two intervals, 3.89 and 6.7, so we would fail to reject. If we are doing it as a two-tailed hypothesis, then this CI approach is used, and for one-tailed test other options are there like sign test. We'll see it in a moment. But if you are doing it as a two-tailed test, then this approach is just fine. Let's also look into this sign test. So assume we have the random sample y1 up till yn from a population with median that's equal to m. So any number of a sample can have any number of elements in it. The sample size can be anything between 1 to n, and the median is given by m. So if we let the null value of m to be m naught, the median under the null, and we define w that's equal to yi minus m naught, so that is the median. So we take every number and subtract the median from it, and we get the values, the w's. So those w's will be either positive or negative depending upon if they are more than median they will be positive, if they are less than median they will be negative. And the sign test statistics we define is b which is the number of values greater than m naught, that is the positive value. Since we are doing it this thing as a as a one tail to the right test, so this test statistics here will be we are looking for those positive W's. So B is the actually the number of positive WI's. WI is the difference between each number to the median. So obviously the numbers bigger than median, they should be positive. Because the WI's are independent, each WI has an equal chance, 50% chance of being positive and 50% being negative, whether m is equal to m naught. So under the null hypothesis, uh, we can use it, this b, we can call it a binomial random variable, because there is an equal chance of getting selected. The probability is 0.5, that stays the same. And we can use the percentiles in table 4 as we did before in the previous session where we did this confidence interval based test for the medians. And we can construct a rejection region to test our hypothesis. So here our null hypothesis is m median less than equal to 5 versus HA median is greater than 5, and we construct the table again and we find those numbers. So for the lower confidence interval, or this thing, C alpha 1, now we go for this one-sided at n, and coincidentally this was also 7, and for the upper it should be n minus C alpha 1n, so that's 25 minus 7, so here it's 18, so the number is 18. So we reject the null hypothesis if b is greater than n minus C alpha 1n, that is 18. So if b is greater than 18, if positive numbers are greater than 18, we will reject the null hypothesis. So we check for those WI's, so which are yi minus m naught median, yi minus 5, so we check for every number. So 1.2 minus 5, that's minus 3.8, 1.2 minus 5 minus 3.8, and so on. So we get all these negative numbers up till here. So numbers bigger than 5 will give us the positive numbers, so we will simply collect them and we count their numbers. So total numbers which are positive here are 13, so b is equal to 13. So now we compare this b with this number 18. As we said before, if b is greater than this n minus c thing, and we found the number was 18, so if b is greater than or equal to 18, we will reject the null hypothesis. Here it's not greater than 18, our number was 13, so we failed to reject the null hypothesis. There is also a large sample approximation to this. If n is greater than 50, which are the values larger than what we have in table 4. Table 4 we have the values up till 50, and in if it is greater than 50, we can use this large sample approach. So we come up with a test statistics as BST. So that's equal to b minus n by 2 divided by square root of n by 4. So here it's b was 13, 13 minus 25 by 2, n was 25, and divided by square root of 25 divided by 4. So our number is 0.2. In order to reject the null hypothesis, this BST should be greater than or equal to z for at 0.05, which is 1.96. Our number is 0.2. In order to reject, it should have been bigger than 1.96. Our number is smaller than 1.96. So we fail to reject the null hypothesis. So that's how we do these non-parametric tests. There are others also, and but so far as this course is concerned, we will just look into these two, just to let you know that there exist these non-parametric